Okay, so this question asks us to calculate the top left entry in the output. And that little star that we see in between the left matrix and the second matrix is actually called the convolution operator. So we can like multiply two matrices, but now let's talk about how to convolve two matrices. And this is actually like the fundamental mathematical operation occurring inside CNNs. So on the left, we actually have an image. Let's think of that as an image. It's a 4x4 image, and we know at every location or pixel in the image, we have a number. So we can see that on the left. And on the right, let's say that is a sample 2x2 filter or kernel inside a convolutional neural network. So how do we actually convolve that image on the left with the filter on the right? Imagine taking that 2x2 filter on the right and overlaying it on top of the image, specifically every 2x2 block in the image. So we can see the first 2x2 block over there, and if we slide it to the right 1 unit, another block over there, and another block over there. And now that we've gone left to right once, we want to start going down. So another block over there, and over there, and over there, and then over there, and then over there, and over there. So hopefully the animation helps with seeing how the filter is sliding over the image. But to get the top left entry in the output, we actually just care about that very first 2x2 block. So we actually overlay the filter over that 2x2 block over there, and then we look at the corresponding numbers, we multiply them, and then we add them all up together. That is simply how the convolution operation is defined. So we actually go ahead and take 4 times 1, and that gives us 4. And then we have 4 times 2, and that gives us 8. So 8 plus the 4 we had at the start, now we're at 12. 0 times 0, nothing, so we're still at 12. And then we do 4 times 2, which is 8. So now we have 12 plus 8, which is 20, and that gives us the answer. So this next question asks us to find the shape of the output. So assuming a stride of 1, that's just how many units left to right and top to bottom do we slide the filter. If we assume a stride of 1 and we have a 2x2 filter, the 2x2 filter on the right, and we have 4 rows and 4 columns in that image on the left, then we can clearly see that going left to right, you can only fit that kernel 3 times, and going top to bottom, you can only fit it 3 times. So that animation that we actually went over on the first question, where we actually showed it going left to right and top to bottom, we would actually end up with a 3x3 output. So this question asks us which algorithm is used to update a filter's numbers or entries during training. And we have an arrow pointing to the filter, which is actually the second thing in that convolution operation. The first thing is the image, the second thing is the filter. And the thing on the right after the equal sign is the convolved output. So vocabulary terms are not super important, right? Usually actually understanding the concepts and everything is more important than knowing the name of an algorithm, but this one's actually super, super important. It's actually the first machine learning algorithm I recommend you learn. And I'll actually link a 5-minute video that I have on my channel explaining this algorithm if you're not super familiar with it. No like absurd, crazy calculus proofs or anything like that. And this algorithm is called gradient descent. This is the algorithm used to actually train neural networks and actually update them to make them more performant and actually increase their accuracy. Okay, which of the following statements about CNNs is true? First statement says gradient descent, the training algorithm for ML, doesn't work on CNNs, but that's kind of implying that it only works on normal neural networks, so to speak. The diagrams like this that you may have seen before, which are basically just linear regression, by the way. And I actually have a full explanation of linear regression and neural networks that I think is one of the best explanations out there, and I have it on this channel. I'll link it in the description. But this is false. Gradient descent works fine on CNNs, just like normal NNs. And the next choice says each filter is sequentially applied, transforming the input image to the output. So that one's kind of implying that, let's say we have a filter, and CNNs are going to have many filters. And we actually apply one filter and we get an output like that on the right, and then we apply another filter to that output, and then we get another output, and then we actually apply another filter, and it just keeps going sequentially. This is actually false though. That is not how a convolutional layer works in a neural network. And we're about to get into how it actually works. And then the next choice says each filter is independently applied to the input image. So we have a bunch of different filters and they all get applied to that same original input image, and independently or in parallel, they learn a pattern separately. They're not sequentially applied, it's a parallel thing. That is actually how convolutional layers work. And through training, we actually end up finding that each filter will typically learn something different. And the last choice says CNNs contain only convolutions and no other layers. This is actually false. Of course, convolutions are the main component of CNNs, but they can contain the linear layers, they can contain these nonlinear functions, they can contain pooling operations, they can actually contain these other things, which if there's interest, I can make like specific videos on the other parts of convolutional neural networks, but they can contain other things, not just convolutions. So this is the answer choice. If you found this video helpful and you want to help this channel grow so that other machine learning enthusiasts can find this channel, there's a couple things you can do. One, you can subscribe to the channel, and two, you can go ahead and share this video with someone who might find it helpful. And hopefully, I'll see you soon.